This video is going to be the Chemical Reactions Part 1 video. The learning objective, the standards are 8.1.4 and 8.1.5. The main goal of this video is to help again to further in explaining how atoms join together forming molecules and compounds and how that depends on the electron arrangement. The actual parts of this video, we're going to talk about some of the vocabulary from Glencoe's Chapter 7. We'll talk about the basic chemical reaction we talked about in class, and we'll also look at how to count atoms and how to understand chemical reactions and balance some equations. So the vocab, physical change, we have a change in size, shape, or the state of an object, but not changing the actual object. An example that we talked about in class would be folding or ripping a piece of paper. It's still paper, even though it's changed its shape or size. Another example would be water. If it's frozen, changing into liquid water, it's still water, even though it's a different state. A chemical change, on the other hand, is a change from one substance into another with different properties. The evidence of seeing whether something happened like that would be changes in color, odor, or the energy that's given off or received in the example or in the reaction. A chemical change example we talked about would be burning paper. The paper changes from a piece of paper to ash and smoke and light and energy, so it's going from one substance into another. Another example would be if you put a nail outside and it gets rained on, the nail can turn to rust. So it's a chemical reaction where the nail goes from iron to being actually a different substance, a different element. Other vocab, chemical reactions. It's basically the process of chemicals changing, or the process occurs when compounds change their bonds and create new different substances. An equation is just a summary of what that is using the symbols and numbers, showing how many atoms are involved in this process. Reactants are the stuff that exist, the substances that exist before a reaction. I like to call it the stuff you start with, and products are the substances formed from the reaction. Now we get to counting atoms. In counting atoms, we're trying to figure out how many atoms there are on both sides of the reaction. And there's some rules. The first rule is subscripts. We've talked about this before. A subscript is the small number after the element, and it tells you how many there are. Okay? And if there is no subscript, you know it's 1. So on our first example, H2O, we know there are 2 H's, 2 hydrogens, and 1 oxygen. The other example, hydrosulfuric acid, H2SO4, we have 2 H's, S equals 1, O equals 4. On these problems, anytime you get a new capital letter, you're running into a new element. So that means everything after that will be a new, or that will all be the atoms. The next step is if you have a parentheses mixed with subscripts. This means you multiply everything inside the parentheses times the subscript outside of the parentheses. On our example, we have iron 3 and then PO4. We have 2 of those ions combined with the iron, or 3 irons. So I have Fe equals 3, P equals 2 because I have 2 times 1, and then O equals 8 because I take 4 times 2. The last one we have, this is the new one, is a coefficient. A coefficient tells how many of the compounds you have. So it multiplies all the atoms individually times that. So I have 2 compounds of H2O, or 2 molecules of H2O. That means I have H equals 4 and O equals 2. 2 times 2 is 4. 2 times 1 is 2. The other example, if we take our other one, we have Fe. We had 3. In the compound, we had 3. But we now have 3 compounds, so 3 times 3 is 9. The phosphorus, we had 2 of them in the compound. Now you multiply that times 3, so phosphorus turns into 6. And oxygen, we had 8 in the compound. 4 times 2 was 8. And then you multiply that times 3, so 8 times 3 is 24. So this is how you count atoms. We'll do a couple more examples. This comes from the Counting Atoms Extended Number 1 assignment. These are the ones that we worked in class. We'll go through those again. So in the compound PbOH, there's one Pb in the compound, but we have 3 compounds. So Pb equals 3. There are 2 oxygens in the compound, but we have 3 compounds, so oxygen equals 6. Hydrogen as well has 2 in the compound, but there are 3 compounds, so we have hydrogen equaling 6 atoms as well. The next example, H, there is only one compound or one molecule of H2SO4, so H equals 2, S equals 1, O equals 4. If there is no number out front, then you know it's just whatever the atom's normal atom counting rules apply. The next one, copper, there's 1 in the compound, but we have 3 compounds, so Cu equals 3. Chlorine, we have 2 in the compound, but there are 3 compounds, so 2 times 3 is 6. On this example, first thing we want to do is count up how many of each atom there are. So there are 2 C's in the compound, C1 and C2, and then we have a total of 2 compounds, so C is 2 times 2, which is 4. Hydrogen, I have 3 here and 1 here. That gives me 4 inside the compound. We have 2 compounds, so 4 times 2, hydrogen equals 8. Oxygen, we have 2 molecules, or 2 atoms of, or 2 elements, 2 atoms in the molecule, and then we have 2 compounds, so we have oxygen equals 4. Again, carbon simply has 3 because 3 times 1 is 3. Oxygen, 2 times 3 is 6. Our last example, this one's a little different because we have a plus sign. This is starting to look more and more like an actual equation. The whole point of this is to figure out how many atoms are on either side of an equation. So I have 2 K's, 2 F's, and Cl I have 2, because this coefficient in front of the Cl is actually a 1, because this is one compound, this is the other compound. So the 2 does not distribute all the way over here. It just multiplies everything inside of its compound. So that's examples on how to count atoms. We're going to talk a little bit about what the point of a chemical equation is. The whole point is to easily explain a long-winded, long reaction with symbols. So here we have the reaction of the reactants of 1 molecule of methane and 2 oxygen molecules produces the products of 1 carbon dioxide molecule and 2 molecules of dihydrogen monoxide, which is very long. It's actually a little bit easier and faster to write it with the chemical symbols. Now, do I expect you to know every symbol on here? Not necessarily. Normally the formulas will be given to you of what the atom or what the molecules are. On the left hand side you have the reactants, the stuff you start with. On the right hand side you have the products, and anytime you read this arrow you should say produces. The arrow means produces. Here's some more, looking at this picture we can actually simplify it a little bit. We have 2 sets of O2. There's one set of O2 and another set of O2 on the reactant side, so we can combine those with the coefficient. And then on the product side we have 2 sets of H2O. The ones are not necessarily needed, so we can drop those off, and our first equation simplifies as CH4 plus 2O2 produces CO2 plus 2H2O. Methane plus oxygen produces CO2 plus 2 water molecules. And that was the equation that we talked about when we were a combustion reaction, when we talked about the candle burning in class. So we'll do one more, a couple more counting atom pictures. On the left hand side we're going to count up how many atoms are on the reactants. Right now we have 1 C, so it's going to be 1 carbon. We have 4 H's next to it with the methane, and then I have 2 times 2, so I have 4 oxygens. On the product side I have 1 carbon. Hydrogens, I have 2 sets of water molecules, so 2 times 2 is 4. Oxygens on the entire right side, I have 2 in the CO2 and 2 in the H2O. You add those together and you get 4 atoms of oxygen. And as I look at this, I can see every atom that I have on the left is equaled on the right. If it's like that, we say that this equation is balanced. And only balanced equations are the ones that actually happen in nature. So the question that we had on our packet was, are atoms created or destroyed in a reaction? And then how do you know? The answer is they are not created or destroyed. If there's exactly the same number of each type of atom in the products as there are in the reactants, that means we didn't gain or lose any atoms. The picture on the right is kind of showing that. It's saying that we had an equal amount of C's on the left-hand side as we do C's on the right, equal amounts of oxygen molecule atoms and oxygen atoms on the right. So it's balanced if they have the exact same number on either side. Also, we know that this mass, the amount of mass that's on the first side of the reaction, is equal on the other side. So the mass and the numbers of atoms stay the same. Physical changes, like changing state from solid to liquid, the substance itself doesn't really change. How is a chemical change different from a physical change? In a chemical change, we have a new substance formed. So we don't get new atoms, but we have new combinations of atoms with different properties. But in a physical change, it only changes the size, shape, or the state of the matter that it is. But you still have the same stuff. A couple more examples. This one is a different reaction. It's another combustion reaction because we start off with C's and H combining with oxygen, producing CO2 and water. On the left-hand side, we have 3 carbons, we have 8 hydrogens, and we have 10 oxygens. On the product side, we have 3 times 1 is 3 carbons. We have hydrogens, we have 4 times 2 is 8 hydrogens. Oxygens, I have 4 from the water plus 6 from the CO2, giving me 10. So we can see that this equation is balanced because the number on the reactant side equals the number on the product side. Another example, C equals 4 because I have 4 of them here. H equals 10 because I have 10 in this hydrocarbon molecule. Oxygen is 26 because I have 13 times 2. The products, what is produced, I have, whoops, there's a typo here. This should probably be a, oh no, actually this is, we're trying to count. We're seeing if this is balanced. On the left-hand side, I have 8 carbons. I have 20 hydrogens. And then I have 8 times 2 is 16 plus 10 oxygen, so I have 26. So real quickly, looking at this equation, we can tell it is not balanced because the numbers don't equal each other on both sides. So this reaction will not occur as written. However, if we were to change this little 1 into a 2, if we add a coefficient, we can change the number in front, but we can't change the subscripts. If I change that to a 2, I now have 8 carbons and 20 hydrogens. So this equation is balanced. Okay? When you're balancing, you only change the numbers in front, the coefficients. You can't change these other numbers, the subscripts, because if you change those, you're not actually talking about the same reaction occurring anymore.